Yep.
You
So
see a
yeah,
single slide, right?
yes,
Just
we can see your slide. Yep.
clarification. Yeah.
Great. So thank you very much, Monika. Please go ahead.
Well, thank you so much for the invitation to be, I suppose, virtually here in Pittsburgh. um, the title of my talk today is Engineering Quantum Spin Models with Atoms and Light. And for context, I'd say that one of the sort of exciting recent developments in this field of cold atoms and optical control is the ability to have extraordinarily good control over the positions of individual atoms in 1D arrays, 2D arrays, even 3-dimensional structures, thanks to the ability to control atoms with laser light. In my talk today, so in order to sort of go beyond these beautiful pictures and start doing physics, the sort of complementary thing that one needs is control over the interactions between the atoms. And in my talk today, I will be focused on programming the interactions between atoms with laser light. Specifically, one starts to need long-range interactions on a scale that is long compared to sort of the wavelength of light, where one can optically address and manipulate the atoms. And I will so far be starting to ask the question, can we use use systems where we can use light to turn on interactions to start to also gain a high degree of programmability? Okay, and so just so that you're not disappointed in what I'll be talking about today, we won't be working with these individual atoms, and most of what I'll describe can be understood in a more semi-classical picture, working with larger numbers of atoms. But these are techniques that ultimately I envision coming together in terms of the control of the positions and the control of the interactions. So, okay, so how will we, first of all, why do we want to control the interactions? There are a few different directions that we're interested in my group, ranging from what types of quantum many-body states can we make in a controllable way? Can we build Hamiltonians that are of interest for quantum simulations of phenomena ranging from condensed matter physics to perhaps quantum gravity? But the one that I'll try to focus on a bit more today are potential directions in the field of quantum approaches to solving classical optimization problems. So can you encode some classical cost function in the energy of a quantum system and perhaps use the quantum system to help you solve that? So I always like to have sort of a concrete example in my mind. I'd heard this idea of using quantum spin models for optimization at an abstract level for a long time, but I never sort of knew exactly what types of problems could you solve. So here's just a very concrete example to sort of get us started. So, and this is an example that many of you will have encountered. My optimization problem might be one of optimally scheduling lectures that students want to hear, right? So suppose that I have 2 time slots, 2 parallel sessions in a conference, a morning session and an afternoon session. And every participant can attend one lecture in the morning and one in the afternoon. If I'd like to sort of optimally schedule the lectures, what I might do is draw a graph where each vertex is a lecture, and each edge is weighted by the number of people who would like to take both of these lectures. And if I want to schedule things well, what I should do is, if there's a very heavy edge between these 2 nodes, I should place one of those lectures in the morning and one in the afternoon so that all of these people can take both. So the optimization problem is somehow to cut the most heavily weighted edges on the graph, and you can immediately see that what it looks like is some kind of a spin model with anti-ferromagnetic interactions. Right? If I have a heavy edge, I'll color one red and one blue, or equivalently think if one of these spins is up and the other one is down. So this brings us to sort of a very generic class of problems that can be encoded in as minimizing the energy of some kind of an Ising model. And if you'd like to start to investigate whether quantum mechanics can help with this class of problems, then the next thing you'd like to do is perhaps add some non-commuting terms to your Hamiltonian, like a transverse field, to make this a quantum system. And and there are many open questions about whether quantum mechanics can help and how. But certainly the key ingredients that you need to start to investigate these are some spins that we might encode in cold atoms, long-range interactions between them, and some way of programming the structure of those interactions. And so this aspect of programmable long-range interactions will be the subject of my talk today. And specifically, I'll talk about two different physical systems we work with in my lab. One is one where we couple atoms to Radberg states in order to generate interactions that are long-ranged in the sense of extending over several microns, but still have a sense of locality to them. In a second system that I'll get to in the second part of my talk, we'll be dealing with interactions that can actually extend over millimeter scale ranges. They're highly non-local, and those will be mediated by photons in a cavity. So let's start with this first system of the Radberg atoms. So the basic idea, right, is that if I have a ground state atom, cesium atom, that's about the size of this blue dot, if I excite it to a Radberg state, it will be the size of this big red circle, much larger and more polarizable, and the van der Waals interactions between these atoms scale as the principal quantum number to the 11th power. And that readily gives me very strong interactions on the scale of a few microns. And there are a number of experiments that are harnessing these interactions in various ways to do beautiful physics. And the thing I'll just briefly comment on is that there are a few different ways of taking advantage of the Radberg states, several of which involve encoding a spin such that one or both states is directly in the Radberg manifold. I'll give an example where we're actually encoding the spins in the ground states of cesium atoms. So ordinarily these atoms are non-interacting, but by turning on light to couple one of these states off resonantly to a Radberg state, we can controllably turn on an interaction. And the benefit of that is that it does give us a nice aspect of optical control. So the experiments we've done so far are in the simple setting of a cloud of atoms in an optical dipole trap. And we illuminate some portion of that cloud with a laser that is, so we encode spins on the clock transition in cesium. We illuminate a portion of the cloud with a laser that couples this upper clock state to the Radberg manifold off resonantly. So the first thing you get from this off resonant coupling is an AC Stark shift on the spin up state. If I have two of these atoms, and they're very far apart, I'll also simply get that same AC Stark shift. But if I start to bring the atoms together, and they're both in the spin up state, then at fourth order in perturbation theory, there's a process involving exciting both of those atoms to the Radberg state and de-exciting them that is suppressed when I bring them together because the strong Radberg-Radberg interaction means I can't excite them both. And that means also that the AC Stark shift is suppressed as we bring these atoms together. And that results in an interaction, an effective interaction now between the ground state spins. Okay. And in particular, the form of the interaction is an Ising type interaction. And one way we can see that what you expect that to do at a mean field level, each atom is, in our gas is interacting with many surrounding neighbors. And so you'd expect essentially each atom, let's say if it's in the, if I initialize an atom, let's say along X, the rate at which it processes will depend in some way upon how many surrounding atoms are in the up state or the down state. But that also means that quite generally, if I initialize a spin polarized state with some tilt, I should see a precession rate that depends on the tilt of that spin polarized state, because it depends on the number of neighbors in the spin up state. So here's an experiment. This is actually just showing the average magnetization in some region of our atomic cloud. Initially, all of the spins are polarized at some tilt on the meridian of a Bloch sphere, and as we turn on light, and as a function of time, we in fact see a tilt-dependent precession rate that tells us that these Ising interactions are present. Okay. We can also look at the spatial dependence of this effect. So here I've just shown you basically essentially the magnetization for these different initial states at different times, and you see this sort of initial meridian get twisted as a function of time. And another way to visualize that is that if I look at sort of the phase, that's color on this plot, as a function of initial tilt, it has the opposite sign depending whether I'm tilted sort of more up or more down, right? That's this red and this blue. But if I now look, for example, versus position in the cloud, I can also see that this effect, this twist effect that's shown by the gradient from red to blue, is strongest in the center of the cloud and then falls off in a way that I can understand nicely from the profile of this light field. Okay, so that's nice because that shows us that we have this optical control of the interactions. And that so far is the Ising interaction, and I said that the next ingredient you might want is the ability to add a transverse field. So we can also do that in our system. In our system, a transverse field is just a microwave coupling between these two clock states in cesium. And it turns out that it's convenient for us to introduce the interactions and the transverse field in a sort of a Floquet scheme, where we alternate between them. Okay, so we alternate in short pulses, Ising interactions, transverse field, Ising interactions, transverse field. If we do this quickly, which is what we're doing so far in our experiment, then I can simply think of it as an effective Hamiltonian that's the sum of these two terms. Okay. So let's see whether this behaves in a sensible way. So, okay, as a simple case to start with, let me turn off the interactions and just turn on the transverse field. And what we're going to look at are just the dynamics when we, again, initialize a number of different states tilted on this block sphere. The blue squares here are the initial states, and the circles are the trajectories after one or more pulses of this Floquet sequence. And in this case, you simply see the spins beginning to precess about the x-axis because of the transverse field. Fine. One thing we can think of as sort of an interpretation of this is there's a single fixed point, which is the x-axis, which I can also think of as the ground state of this Hamiltonian, right? So there's some precession about this fixed point. If I start to turn on interactions, what we see is that the fixed points of the dynamics begin to move. And in particular, here I've turned on a ferromagnetic Ising interaction. The sign doesn't matter for the dynamics, but I've turned on an Ising interaction, and there are two new ground states that are above and below the equator, and that manifests itself in the spins beginning to precess about those two new points. So we see this bifurcation in the fixed points. That's some signature of a paramagnetic to ferromagnetic phase transition in the ground states of the model. Okay, so we can actually take this one step further and look as a function of position in the atomic cloud. And to tell the truth, actually, to vary the interaction strength before, we were actually just looking at places with different light intensities. Okay, so again, for interactions only, we saw this picture where again, the vertical axis here was the tilt of our initial state. The color is the phase after some period of evolution. But when I turn on my transverse field, what I can look at is where is the phase 0. So 0 means the phase didn't change. And this contour that's white, where the phase is 0, is a signature of the fixed point of the dynamics. And so we can nicely see that in the wings of the cloud, in the absence of interactions, we have a single fixed point, which then splits at some critical interaction strength into these two new fixed points that represent the ground states of the ferromagnetic model. So I think this nicely illustrates the use of the Radberg dressing approach to give us optical control, in this case over the strength of the interaction, also dynamical control of the interactions. And now, so far we focused on the dynamics, but if you want to now start to explore applications to, for example, optimization problems, okay, first you should go beyond this setting of the gas and have individual atoms that one can observe individually. But one sort of natural extension here is actually to work in the regime where the interactions are anti-ferromagnetic, okay? This then maps onto that max cut problem I said before, or work in the regime where we're particularly trying to solve this model by pulsing between the interactions and the transverse field. Essentially, that Floquet scheme I showed before is really precisely what's known as the quantum approximate optimization algorithm that's being explored for solving precisely these types of problems. So this is one outlook with the system. I'll mention that there are many questions about to what extent this proposed algorithm actually can offer a quantum advantage. So one thing that we've been thinking about actually is other approaches to exploring quantum optimization in this Radberg system. And it turns out that there's another problem that's very natural to encode if one has strong interactions between a collection of spins and a single central spin. And the problem is essentially a problem called number partitioning, which is I have a bunch of objects, they have weights, which would be encoded by the weights of the couplings to the central spin. And the question is there a way to divide them in a way that balances a scale? So I'll just mention that we've been doing some theory, particularly while our labs were shut down, on using this type of a model that's accessible in the Radberg dress system to speed up the solutions to the number partitioning problem, essentially by applying Grover's algorithm, which naturally solves this class of problems for the structure of interactions. And I really encourage you to ask me about this in the questions. Okay, so with that, I've introduced the first platform that we're working with in our lab. And I want to switch gears and say that these Radberg interactions allow for realizing long-range interactions, but nevertheless, there's a significant restriction on the graphs of interactions one can generate because they do decay with distance. And so to go beyond that, I'll introduce our cavity QED platform, where we can have highly non-local interactions. And maybe I'll just ask, should I pause for questions because I'm about to transition, or would you prefer that I keep going?
I'd suggest to keep going. No one has put any questions in the chat, or
Okay.
well, if anyone wants to ask an urgent question, either do that or raise your hand now. Nothing
Okay.
looks urgent, so
I can
please
keep going.
carry on.
There's
Yeah.
just something weird about talking to an empty room. So, okay. So our alternative platform is one where we let spins sort of talk to each other over long distances by scattering photons into a cavity mode. So the general idea is, one way I like to think of it is, if I have a spin-up atom, I can think of that as an occupied site, a spin-down atom is an empty site, and I can make spin excitations hop over long distances in a way that's mediated by light. And to do this in a way that is optically controlled, what we do is we send a drive laser into the cavity, and the drive laser can drive a Raman process where an atom absorbs a photon and flips its spin, and a second atom, sorry, let me say that again. An atom absorbs a photon from the drive field and flips its spin, thereby emitting a photon into the cavity, right? And then a second atom can absorb that photon from the cavity and also flip its spin. We work in a regime where the process, the Raman process, that involves a single spin flip, is off-resonant, but the pairwise process is resonant, and that allows us to generate long-range interactions. So the general concept of having photon-mediated interactions in a cavity, as you've already heard in the previous talk, is not new, and there have been beautiful experiments in Tilman Esslinger's group, and I think you'll hear about Ben Lev's experiments tomorrow. One ingredient that we've been particularly interested in sort of adding to this cavity QED toolbox is having real space observation of the spin dynamics in the cavity. And so the experimental setup looks like this. Okay, there are two mirrors. They're 5 centimeters apart. There's a standing wave in between the two mirrors in which we trap the atoms. So spatially, they're pinned at some position along the cavity axis. And in the first experiments I'll show, they're essentially in a cloud that's sort of order a millimeter long. And we have a lens that allows us to see what's going on inside here. So for example, here's a picture where the horizontal axis is position in the cloud, the vertical axis is time. At t equals 0, we initiated the system with some spin excitations in a particular region of the cloud, and then turned on that drive field and watched what happened. And you see the spin excitations hop over here and back, and there are some oscillations. So these are spin exchange interactions mediated by the cavity that we're directly observing in real space. So far, if actually we can understand these dynamics very well, just by knowing that, you might ask, why do the spin excitations hop here? It turns out we can actually understand that by knowing that the interaction strength between any pair of spins in the cavity is simply the product, in this case, of their couplings to the cavity mode. Now, one thing we might want to do is start going beyond sort of the form of interaction that you just most naturally get and start to program the interactions. And so I'll be talking about different aspects of programmability of these cavity-mediated interactions. First of all, actually, we'll have control over the sign of the interaction. One might want to control the form of the interaction. So far I talked about flip-flop interactions, these spin exchange interactions. But perhaps I also want to realize Ising models. So this would be a nice nod to have. And lastly, I'll get to the spatial structure of the interaction. So I said that so far what we most naturally get in what I showed you is something where these couplings Jij are just products of pairs of couplings to the cavity mode. But perhaps we want to do something more exotic. If you want to make the interactions more local, that'll be one thing we can do. But perhaps you also want to make crazy interaction structures that you can't realize in any other way, like something where the structure of the interactions is best described by thinking of the atoms as living on the leaves of a tree. We haven't done this yet, but we've done some theory on this with Andrew Daly, and this is actually an intriguing prospect for simulations of quantum gravity. So these are some directions we want to go in terms of control. So let's go through these bullet points. So let's start with the form of the interactions. So for now, we'll stick with something where the spatial structure is dictated by the local couplings to the cavity mode. So I'll write the Hamiltonian in terms of some collective spin that's weighted by these local couplings. And we'll ask the question, can we go beyond these spin exchange interactions to also tune whether I have a spin exchange or an Ising coupling? Okay. And it turns out that that's something that we can do in our system. Simply actually by controlling the orientation of a magnetic field relative to the cavity axis. The way that you can think about this is that the magnetic field acts as a quantization axis for the spins. And the interactions I can understand as coming about from essentially a Faraday type effect where the magnetization of the atoms couples to the polarization of the light. And what matters is the magnetization along the cavity axis. So if this field is along the cavity axis, the Z component will couple to the light, and the Z components will interact. If the field is perpendicular to the cavity axis, the spins will precess about it, and either the X or Y component at any given time will be coupled to the cavity, and that turns out to give you this spin exchange form of the Hamiltonian. So in addition, I'll just comment that we can control the sign of the interaction by the sign of the laser frequency. And so at the right here, you see a plot where we've demonstrated those both forms of control, varying the angle of the magnetic field and measuring the Ising coupling decrease and the spin exchange coupling increase in the way we expect when we do that. So you might ask, actually, how did we do this measurement? And this is a measurement where we're looking at the dynamics of the system. So we actually, by some beam that's incident from the side, initialize the cloud with some spin texture where some of the spins are pointing along Z, some of them are pointing along X, some of them are pointing along minus X. We turn on the light and we watch how that spin texture evolves. And so, for example, from the precession of these X and minus X spins about the spins that are pointing along Z due to the Ising interaction, we see this phase evolve, and from the rate and direction of the phase evolution, we can extract the sign and the amplitude of the couplings. And so that type of dynamical protocol allows us to sort of map out the Hamiltonian that we've created. And particularly when I talk about having control over the sign of the interaction, though, you might be interested in thinking not just about the dynamics, which direction do the spins precess, but also about sort of what are the low energy states of the system, right? If I tell you I can control whether I have a ferromagnetic or an antiferromagnetic interaction, you'd like to see that this manifests itself in the spins wanting to align or to anti-align. So that's also something we can do in this system, is to basically initialize the system with all of the spins aligned along some effective magnetic field that's produced by a Raman coupling, and then slowly ramp on interactions and watch what happens. Actually, first, if we do this with no interactions, let me just show you. Here's something where all we've done is ramp the final orientation of a magnetic field, just for reference, right? And so as we ramp that final orientation from downwards to upwards, you see that the polarization of the spins follows, and that's shown here in red and blue. So if we turn on interactions, we do the same thing, but we ramp on ferromagnetic interactions. What you'll see is that this tilting of the polarization from downwards to upwards all of a sudden has a very, very sharp edge because the spins all want to stay aligned. So just as soon as we slightly tilt this Z field, all of the spins flip. Okay, and if you work with antiferromagnetic interactions, is the opposite tendency is visible, a tendency for the spins to anti-align. We can kind of summarize this in a measurement of the magnetic susceptibility of our system. So the blue here is the case of Ising interactions, and we see that the magnetic susceptibility, that sharp edge that I showed you, is manifest here in the susceptibility rising as we approach the phase transition from paramagnetic to ferromagnetic. And one of the interesting features, though, is actually if I do the same thing with spin exchange interactions, I see exactly the mirror image of this curve. And that's something that we actually can understand in this picture where I think roughly of having essentially some collective spin that's coupled to the cavity mode. So in the simplest case, I in fact have these weighted couplings, so it's a bit more complicated. But in the simplest case, if I had uniform couplings of all spins to the cavity, then I could actually write for example, an Ising interaction of one sign, this Fz squared term, as being exactly equivalent to an XY interaction of the other sign up to some term that just depends on the total spin. And so that symmetry is actually what explains this similarity of the susceptibility for the Ising in the XY case. But one thing that we are actually interested in is, in some sense, the fact that we see that symmetry means the system is a little bit boring, right? It's acting just like one big collective spin, and so maybe it's not so useful for studying any many-body physics, right? So I'd really like to enter a regime where I can't just think of this as a single quantum object. So the question is basically, can we see a difference now between these ferromagnetic, let's say, Ising interactions and anti-ferromagnetic XY interactions, or vice versa? Okay, so here's an experiment we did to start to probe that. It turns out that we can start to sort of break the symmetry by adding an inhomogeneous field along the z direction, an inhomogeneous magnetic field along z. So this is a non-interacting system. We have an inhomogeneous magnetic field. We turn on the interactions. Sorry, this is a non-interacting system. At t equals 0, we initiate a spin polarized state, and then we watch how the spins evolve, and you'll see, due to the magnetic field gradient, a spiral texture forming in the orientations of the spins. Okay, so what happens if we turn on interactions? So actually, as soon as we turn on XY interactions, in this case ferromagnetic XY interactions, you see a dramatically different picture. It actually looks very boring. But the reason it looks boring is that the spins are now all staying aligned, despite this same magnetic field gradient. So we see, by contrast, if you do this with Ising interactions, there's no such effect. So this is basically showing as a function of time how much the phase has wound across the cloud. In a non-interacting or Ising system, it's winding in a way that's set by this field gradient, but this winding is completely suppressed by the XY interactions. So this is actually a nice effect that has potential implications, actually, for preserving spin coherence. And one way to understand it is that, again, we have almost the same Hamiltonian, but the difference is that in one case there's a term that depends on the total spin. So you can think of this as there's an energy gap between manifolds of different total spin, and that energy gap prevents you from dephasing. It wants to keep you in a manifold of fixed total spin. Okay. And so as a function of interaction strength, again, here's kind of just showing how the contrast is preserved in the case where we turn on these XY interactions. This idea of harnessing the energy gap to protect spin coherence was also studied in some very nice work in James Thomson's group, where they spectroscopically found evidence of the gap. A nice feature of our experiment is that we can directly observe its effect on the spin dynamics. Okay, so this could have implications for kind of protecting spin coherence in quantum control applications, particularly if you need the light anyway. For example, to make some entangled state. It's great if it also helps you protect the coherence of the system. Everything I said so far you can actually understand quite well in a fairly classical picture, right? Of the spins wanting to stay aligned with each other. So let's go towards something that looks a little bit more quantum. So one of the nice features of our system that I sort of swept under the rug up till now is that we actually have a spin 1 system. And so you can look at things other than just the sort of vector aspect of the magnetization. So for example, we can initialize all the spins in the 0 state, turn on spin exchange interactions, and watch what happens. And what happens is that if I now look as a function of, well, in this case, just look at many repetitions of the same experiment, what I'll see is that on certain shots of the experiment, I see large populations being transferred into the plus and minus 1 states of the spin 1 system. Okay. And so you can think of this, so there are large fluctuations, but they always appear to be correlated, right? And you can think of this as essentially a light-mediated analog to phenomena that are observed, for example, in BECs, where two spin m equals 0 atoms collide and form a plus one minus 1 pair. But in this case, it's not a direct collision. It's a long-range interaction mediated by light. This form of interaction can happen on a millimeter length scale. And so that opens up some interesting directions where one can start to ask, in the BECs, this mechanism has been used to generate highly entangled states that are of interest for quantum metrology, we can start to ask, can we use the light to spatially sculpt the form of the correlations that one gets in systems like this? Since I wanted to address the theme of computation, I'll mention that there are also ideas for using these types of pair creation processes to study graph theory problems like graph matching. So that could be an interesting direction. Okay, but so far, again, I said in principle we can use the light to control something about the structure of the interactions and the correlations. I haven't shown you yet that that actually works. So let's take this one step further, and actually to start to explore whether we can control the spatial structure of the interactions. It turns out to be cleanest to work not just in this extended cloud I showed you before, but in an array of small ensembles that are regularly spaced. So we now have in the cavity an array of, let's say, currently 18 small ensembles that have 1,000 atoms each. The 1,000 atoms give us a collective enhancement in the interaction strength. And what we'd like to be able to do is to really control which ensembles talk to which ones. And there's actually a very natural scheme for starting to control at least translationally invariant forms of the interaction. So our modest goal will be to have arbitrary control over translationally invariant couplings in this system, and that actually can go to even fancier interaction graphs if you start to control the positions of these ensembles. Okay, so how might we do this? The basic idea that we've started to look at in the spin-1 system is, first of all, turn off the long-range part of the interaction by applying a magnetic field gradient. So earlier I had something where I could start with two m equals 0 atoms, and they could form a +1 -1 pair at any distance in the cavity. If I turn on a magnetic field gradient, though, that process will only be resonant if the atoms are essentially close together, right? And so we can see that if we look at spatial correlations between the +1 and the -1 atoms in this pair creation process, by turning on the magnetic field gradient, we basically restrict those correlations to appear locally. And that, naively, you might expect that to give you correlations just along the diagonal in this plot. Okay, they're slightly off diagonal. That has to do with a quadratic Zeeman shift. I won't get into that. But this we can actually understand very well. So we've shrunk down the correlation length here. And now we can start to ask, can we turn back on the long-range part, but in a controllable way? Okay, so as a first step, what we do is instead of driving with just a single frequency, we drive with two different frequencies. And they're separated by some amount that corresponds essentially to the energy cost to form a +1 -1 pair or have a spin exchange process at a given distance, okay? And so when we do that, in fact, we start to see correlations appearing at precisely that distance between the +1 and -1 populations in the cloud. And lastly, we can now vary the frequency spacing, and this is kind of very, very new data. They just loaded the atoms into the array and checked theoretically you expect now to see the correlations appearing at a distance that's set by the frequency spacing between these two sidebands. And in fact, this very first data set very nicely matches that theory. So the generalization of this would be that a multi-frequency drive basically enables arbitrary control of these J of I minus J coupling, so the coupling versus distance. This, we've been thinking about using that for toy models of quantum gravity together with Andrew Daly, ways of making information spread exponentially fast from 1 to all degrees of freedom. And I think an intriguing question here is whether more generally one can think about designing the interactions to sort of efficiently explore a large Hilbert space, and maybe that has also some computational applications. So with that, I'll just summarize and say I've shown you two different physical systems where we have programmability of various aspects of the form, the sign, the interaction graph, spatiotemporal control of interactions. And in terms of kind of computational directions, we're interested in applying these systems to explore problems like number partitioning, max cut, perhaps graph matching. Two approaches that are definitely natural to employ in our system are Grover's algorithm and this QAOA approach, but I'd also love to think about whether there are approaches that, for example, are more naturally dissipative, harnessing that aspect of the cavity system. So with that, I put these in purple because I encourage you to ask me about them. But with that, I should just thank my team, and particularly the folks in blue have done the Radberg experiments, the folks in red have done the cavity experiments. and Galit is an undergrad who has led the theory on quantum optimization. So with that, I will conclude and take any questions.
Thank you very much. So I see already there is a question from David Snoke. So David, you want to go ahead?
Yeah. Let's see, can you see me? I thought
Yeah.
I would, just so you can tell there's actually some people out there that are watching. So yeah, just trying to wrap my head around these long-range interactions. And one thing that I guess that my question is this the right picture that I should have? That essentially you have to have the time scale for a round trip time of a photon in the cavity be short compared to all the other time scales, in which case these interactions look essentially instantaneous. And if there was a real time lag, for the photon to go out, bounce off a mirror and come back again, then that would give you some kind of weird, retarded interaction that could be confusing.
Yeah, that's exactly right. So there is a very large separation in scale between the actual time for the photon to propagate and the time scales of these interactions that we're generating. And it's, in fact, the interactions are slow not only compared to the round trip time, but also to the lifetime of the photon in the cavity. And so, yeah.
Yeah, okay, because that is a potential difference with the polaritons, is that you really do have quite a big time separation between those scales.
Absolutely, yes, yeah. Mm-hmm.
Okay, so there's a question, or someone in the chat asking me to ask you the question you want to be asked. I'll ask you that in a moment, but actually there's another question from Vincent, and then I have a question myself. So Vincent, wait a moment, I need to unmute you, so I need to find you. Here we are. Vincent, can you unmute now?
Great, Monika, very fascinating talk. So I'm particularly interested in this cavity system with the photon mediated interaction, long-range interaction. Is the system fully homogeneous? So my question is like, because your photon intensity would be spatially non-uniform, right? So the interaction mediated by photons would be I guess my question is how uniform the interaction mediated by photon will be.
Yeah, this is a very good question. So
yeah, the second question would be, would it be able to, are you doing the 2D or 1D? I'm just trying to get the full understanding of the picture. Would it be possible going to a uniform 2D case, right? So that's a 2D question.
Okay, so let me start with the first question.
Mm-hmm.
So in the earlier experiments I showed in the cavity, such as this one here, mm-hmm. So actually, first let me describe the cavity. So the cavity has a Rayleigh range that's about 1 millimeter. So that's sort of the characteristic length over which the coupling can be uniform, and beyond that, there's an inhomogeneity that starts to matter. So in this first set of experiments, actually our atomic cloud, the center of the cavity was about here. And the atomic cloud here, this is actually in millimeters, I guess it doesn't say, it's 2 millimeters long. And so you see a substantial gradient in sort of the rate at which the phase is evolving here. And that's actually coming from the fact that there's a gradient in the interaction strength. And so I wrote down this weighted spin, and those weights basically had to do with the local intensity of the cavity mode. Okay, so nevertheless, though, we have this kind of millimeter scale region, if we center ourselves at the center of the cavity, where the interactions are very uniform. So if we want to make them non-uniform, we can do that in this way. But if we want to make them uniform, and that's what we did later on in this array experiment, we're working basically in a regime where this total length is 1 millimeter, so we're only going sort of half a Rayleigh range in each direction from cavity center, and that gives us quite uniform interactions. And if you really want to be, in principle, you can compensate for any non-uniformity by driving from the side and having some extra control, but this is actually already quite uniform. So, right, so then when we start to go to these models that I say are translationally invariant, that's true in the approximation that the couplings to the cavity.
That's great, yeah. Mm-hmm.
In terms of 1D versus 2D, so physically the system is 1D because the cavity mode is only 10 microns, about 10 microns wide in the center. So physically the system is 1D, but then you can ask, can I nevertheless do physics that's 2-dimensional? And the cool thing is if you can program in the graph of interactions, then yes, you can actually do two-dimensional physics.
Right.
You know, if I have even just two kind of incommensurate sort of frequency spacings between drive fields, then you already sort of effectively can rearrange these into a 2D lattice. You know, you could imagine playing with the phases of the drive fields to control the phases of the hopping. Yeah, so I think there's lots of neat opportunities for saying, yes, physically it's 1D, but I can sculpt what the actual best way is to think about the geometry of the system.
Thank you. Yeah.
So I think given the timing, I will just ask the question of, could you tell us a bit more about the Grover search algorithm? And
Yes.
I'll leave my other question for some other time.
Thanks. So let me just actually go. So the basic concept again, so I'll just pose the problem again. So the problem that is natural to encode is I have a bunch of objects, they have weights, which in the standard formulation are integers, and the question is, can I essentially divide them into two groups where the weights would balance a scale? Okay, so to say what the general approach is to solving it, I first have to remind you of Grover's algorithm, which I certainly had forgotten until I had to teach it. So the basic idea with Grover's algorithm is you have, sorry, let me just make sure it's clear that what we're doing here basically is if an object is on one side of the scale, that would say it's in one spin state. And if it's on the other side, it'll be in the other state, right? So basically I want to find spin configurations that solve this problem. Okay, so the idea with Grover's algorithm is basically you're searching for a particular spin configuration. And what you need is some kind of an oracle. So the oracle is usually viewed as a black box device that marks the spin configurations that solve your problem. And what it needs to do is basically apply a pi phase shift if you're in one of these solution states. If you can do that, then there's basically one additional operation. So these amplitudes of certain configurations get a pi phase shift. There's one additional operation you do that so basically amplifies then the amplitudes of the things that solve your problem. So the hard part, though, is actually how do you make this oracle, right? Because normally this is viewed as this black box device that already knows the answer to your problem. So the neat thing is that if I have, so the problem, again, is that what I want to do is apply a pi phase shift if and only if some weighted sum of the spins is 0. So now if I imagine I have some Radberg atom, I'll have one central spin that's encoded on a ground to Radberg transition, and I'll have some surrounding spins whose interactions with the central spin I can optically control. So that gives me a Hamiltonian that looks like a coupling between the central spin and these surrounding spins. And what I can do now is say, oh, okay, so the energy of the transition in the central spin is shifted in a way that depends on these weights that I optically control on the surrounding spins. So I can do something where I do a 2 pi pulse on the central spin if my atoms are in the solution state, but otherwise nothing happens because this pulse is off resonant. And when you do a 2 pi pulse on a spin, we all know I rotate a spin by 2 pi, I get a minus sign. So that's precisely the oracle operation that we need. And so essentially this is sort of a natural physical encoding of the Grover oracle for this number partitioning problem. Okay, and then I'll just briefly say, I guess the problem has some neat features where there's a known phase transition in the computational complexity of the problem, and so we've understood sort of how those manifest themselves in the dynamics you would, in the sort of performance you would expect to see in this type of an algorithm, and but the bottom line is sort of with reasonable parameter. So ideally one gets a quantum speed up that's sort of the square root of n speed up, that's the natural performance of Grover's algorithm, and with some reasonable parameters in a Radberg system that are hard but not impossible, one could expect to actually see this speed up in kind of small systems as a proof of principle, and then how to scale it brings us to the problem of error correction. So, but I think it's a nice example of actually having really a physical encoding of a particular problem. It's somewhere in the space between, I would say, digital computation and analog simulation, right? It's an algorithm that was thought about for universal computation, but here's an analog system that kind of naturally implements that algorithm. There's also a cavity fluidity version of it. So with that, I think I've probably used up all my time, and I'll just thank you again.
Okay, thank you very much. That was great.